High above Earth's icy poles, an invisible force moves in silence. Once just a theory, imagined decades before humanity could measure it. This mysterious global energy now reveals its hand in sculpting our atmosphere and flinging charged particles into the vastness of space. It may even be the silent reason why many planets are forever unfit for life. This force is known as the ambipolar electric field, as fundamental to Earth as gravity or magnetism itself. And thankfully, it is not too strong. Or life, as we know it, might never have emerged. Only recently, thanks to NASA's Endurance mission, have scientists finally unraveled this 60-year mystery by measuring the ambipolar field for the very first time. Their discovery proves that Earth possesses not just two, but three global energy fields. Today, join me on a journey to uncover one of nature's most powerful and hidden forces, the ambipolar electric field. A phenomenon that not only fuels the polar wind, but also helps determine whether our planet can remain habitable. Earth's magnetic field, depicted in this video as onion-like layers of lines, helps to shield our atmosphere from dangerous solar energy and damaging cosmic rays. And the gravitational field, shown here as the white glow around our planet, not only keeps us planted on Earth's surface and stops our atmosphere from drifting away, but also provides valuable information in the study of Earth's changing climate, sea level rise, ocean circulation, and much more. As you can see, our magnetic and gravity fields are critical features that help make our planet habitable. And, with the recent publication of an August 28, 2024 paper in the journal Nature, direct evidence has been found for a third energy field, the ambipolar field. To understand this energy field, we need to talk about plasma. Like a solid, liquid, or gas, plasma is another state of matter which happens to make up 99% of all known matter in the universe. Plasma is made of ionized particles which have so much energy, the electrons have separated from their atoms. Plasma is responsible for several well-known phenomena on Earth, like the aurora borealis and lightning. Plasma can form where atmospheric gas density becomes low enough to support the conditions for it, at around 90 kilometers above Earth's surface. This plasma is made up of very lightweight, fast-moving particles, which get trapped along the Earth's magnetic field lines as they move away from the surface. Around the majority of our planet, plasma encounters a barrier that limits its escape into space, known as the plasma pause. Here, plasma co-rotates along with Earth along its closed magnetic field lines. Until the mid-1960s, the prevailing model of our planet's magnetic field theorized that all of the magnetic field lines were closed, and the plasma remained trapped. So, what changed? We went to space. In the 1960s, the first spacecraft flying over our planet's north and south poles could actually detect a supersonic wind of charged particles, plasma, flowing out to space, including positively charged hydrogen and oxygen ions. This observation led scientists to start wondering whether the Earth's magnetic field model should have an open, rather than a closed tail. At the time, scientists already knew that our atmosphere lost some particles to space due to thermal escape. This is a type of atmospheric escape that typically happens when the energy from sunlight heats up particles in our atmosphere, allowing them to reach escape velocity and break free of our planet's gravitational pull, kind of like when a pot of water boils and steam evaporates. So it was no surprise that some particles would be escaping into space. But something didn't quite add up. If energy from the sun were the only cause of atmospheric escape, one would expect the particles that were escaping into space to be heated. However, many in the stream were actually cold, with no signs of having been heated. And yet, they were traveling at supersonic speeds. Scientists hypothesized that there must be another, invisible force driving this phenomenon, and in 1968 the term polar wind was coined to describe it, leading to more research and theories into its cause and effects. The idea of a planet-wide electric field was developed to explain the polar wind. But when this was theorized in the 1960s, it was thought that the force was too weak to detect. And at the time, scientists were correct. The electric potential was so weak, it would require very sensitive instruments to measure, and that technology wouldn't be invented for several more decades. Enthusiasm to measure our planet's ambipolar field was spurred again in 2016, after a clue came from the European Space Agency's Venus Express mission. One of the reasons that Earth is hospitable for life is because of its water, while Venus today is dry and barren. However, billions of years ago, evidence suggests that Venus might have had abundant water like our own world does now. This raises the intriguing question: if Venus once had water, where did it all go? The ESA's Venus Express mission offered a potential explanation when it detected a 10-volt electric potential around Venus, at least 5 times larger than expected. This marked the first successful measurement of an electric field on any planet, including Earth. The electric field surrounding Venus could pull positively charged ions like oxygen out of the atmosphere, draining it of the essential ingredients of water, like a vacuum cleaner siphoning particles out to space. Over time, this could have played a role in draining the planet of its once abundant water. This prompted a question much closer to home. Does Earth have a similar electric field? And if so, why has our planet managed to hold on to its water? The electric potential measured around Venus was around 10 volts. For comparison, a standard car battery is 12 volts. But scientists expected our planet's electric potential to be as little as 0.3 volts, similar to a button battery you might find in a watch, and some 25 times weaker than the electric potential on Venus. It's this difference that may be a key reason why our Earth has been able to keep its water. And that's what inspired NASA's Endurance team to develop a new type of scientific instrument called a photoelectron spectrometer to find Earth's weak electric field. The instrument is designed to measure the speed of electrons escaping from Earth's atmosphere as a way to reveal our planet's electric potential. If you enjoyed the video, don't forget to hit like and subscribe for more awesome content. Earlier I explained atmospheric escape, and I mentioned that particles are able to escape from our atmosphere when they reach escape velocity. That escape velocity is a very specific, predictable speed. But this speed should be ever so slightly slowed by Earth's electric potential. And so by measuring that slowing effect at apogee, or the furthest point in Endurance's orbit from Earth, the instrument would be able to measure the strength of the electric potential around our planet. Such a sensitive instrument would need to be launched at precisely the right location and time in order to ensure a chance at making the observation successful. The Svalbard rocket range was selected for the job. It's the northernmost launch range in the world, located in Svalbard, Norway, a group of islands in the Arctic Ocean. Here, the NASA Endurance team would be able to launch the instrument on a suborbital rocket through Earth's magnetic North Pole. And on May 11, 2022, the team of international scientists did just that, named after the ship that carried Ernest Shackleton's crew in their 1914 attempt to reach the South Pole and cross Antarctica. The Endurance mission launched its suborbital rocket to an altitude of 768 kilometers, collecting data over 518 of those kilometers before splashing down 19 minutes later in the Greenland Sea. During its flight, the instrument measured a change of 0.55 volts in electric potential between 250 kilometers and 768 kilometers. Space scientist Glyn Collinson, the principal investigator for NASA's Endurance mission, said even though half a volt is almost nothing, again, only about the strength of a watch battery, it's just the right amount to explain Earth's polar wind. This first ever direct measurement of the Earth's electric field marked a pivotal moment in our understanding of this fundamental planet-wide energy force. Understanding the forces that govern our lives is key to innovation. For example, with the right application of magnetic force, you can make a pen float in mid-air without using any electricity. But don't just take my word for it. You can see it for yourself right on your desk by checking out today's video sponsor, Novium. Novium hover pens are premium aluminum pens with sleek designs, comfortable writing, and a variety of colors to choose from. The high-end hover pen Interstellar even features a real piece of meteorite embedded in its tip and hovers at a 23.5-degree angle, a subtle tribute to Earth's axial tilt. For fountain pen or rollerball fans, the hover pen Future offers a futuristic design with interchangeable tips and hovers at a 60-degree angle. It's the perfect gift for any space enthusiast and was named one of Time's best inventions of 2022. But now, let's return to the ambipolar field. The ambipolar field exists in what's called the Ionosphere. It's within the upper reaches of the mesosphere that the Ionosphere begins, but its influence stretches far beyond that. Starting around 80 kilometers above the surface in the mesosphere, the Ionosphere continues outward through the entire thermosphere layer from about 85 to 600 kilometers. This is where auroras happen, and high-energy ultraviolet and X-ray radiation are absorbed, creating charged particles. And finally, the ionosphere ends in the lower exosphere, which begins around 600 kilometers and continues out to about 10,000 kilometers from Earth's surface, where it fades into outer space. The exosphere is where many satellites orbit around our planet. As you can see, the ionosphere starts around 80 kilometers above sea level and stretches hundreds of kilometers into space, where it overlaps with Earth's magnetosphere, a region of space surrounding Earth. Within this massive region of the ionosphere is where we find the ambipolar field, which is theorized to begin at around 250 kilometers. While most of our atmosphere is composed of nitrogen, the upper region of our ionosphere is home to lighter elements like oxygen, hydrogen, and helium. When photons from the sun collide with these elements in the upper atmosphere, they can knock electrons loose from the elements in a process called ionization, leaving positively charged particles called ions and negatively charged electrons. Because of the opposite charges of the negative electrons and positive ions, they are attracted to each other and become tethered together by an electric field. It's this electric field that constitutes a major part of the ambipolar field. The electrons within the electric field are so light that the slightest push could send them flying out to space, while the ions are more than 1,800 times heavier than the electrons and sink toward the ground due to gravity. The subatomic tug-of-war works in both directions, but the upward tug from the energized electrons is able to just slightly overwhelm the force of gravity on the ions. The electrons within the electric field are so light that the slightest push could send them flying out to space, while the ions are more than 1,800 times heavier than the electrons and sink toward the ground due to gravity. The subatomic tug-of-war works in both directions, but the upward tug from the energized electrons is able to just slightly overwhelm the force of gravity on the ions. This outward pressure of ionospheric electrons is what creates the ambipolar field, depicted here as the sparkling blue glow around our planet. The upward lift inflates our planet's ionosphere and accelerates some ions enough to escape from the atmosphere, creating the polar wind along our pole's magnetic field lines. What's more, The ambipolar field can achieve this acceleration of plasmas without heating them, providing an explanation for the cold plasma scientists had detected escaping from the ionosphere. A thumbs up helps us a lot, and subscribing means you won't miss what's coming next. It's the bidirectional nature of the interaction between ions and electrons that gives the ambipolar field its name. The Latin prefix ambi means both, and polar refers to the polar regions, where the electric field's effects are felt the strongest. Collinson, the Endurance mission's primary investigator, called the ambipolar field an agent of chaos, stripping particles from our atmosphere away into space. Hydrogen ions make up the majority of the polar wind. They are so light, the ambipolar field's upward force on these hydrogen ions is 10.6 times stronger than the force of gravity, leading the ions to accelerate up at supersonic speeds and escape from our atmosphere above the Earth's magnetic poles. Physicists have found that our planet loses about 3 kilograms of hydrogen gas every second, or around 95,000 tons per year. Additionally, the Earth also loses about 50 grams of helium per second, or 1,600 tons of helium gas per year, a smaller but still measurable amount, and a much smaller amount of other gases like oxygen. However, not all of this is due to polar winds. It occurs through a combination of factors, including thermal escape and non-thermal escape mechanisms, such as polar wind. But don't worry. Despite our planet losing several hundred tons of its atmosphere to space every day, we're nowhere near running out of air. The planet won't run out of oxygen for 1 billion years. It will be another 1 billion years after that, before our oceans will have been depleted of most of their hydrogen. Around 4 billion years from now, our planet may look very similar to how Venus looks now. All of our water will have evaporated, and the greenhouse effect will have become strong enough to melt rock, leaving our planet a dry, lifeless world. Keep in mind that modern humans have only existed on this planet for around 300,000 years. Our species would need to exist more than 3,300 times that length to be around in 1 billion years. While not really important on human timescales, it is still interesting to think about though. And while hydrogen ions may be the lightest and most common type of ion to escape in polar wind, heavier particles also get a boost from the ambipolar electric field, helping to shape our atmosphere's structure and dynamics. How exactly? Well, now that we've measured the ambipolar field, scientists can delve into all of the ways the ambipolar field shapes our atmosphere. Take oxygen ions, for example. These heavy ions weigh half as much when they're immersed in the 0.55-volt ambipolar field. This effect increases the ionosphere's scale height by 271%, which means our atmosphere can remain denser at greater heights than it would otherwise be able to do. Endurance's discovery and measurement of the ambipolar field also provided an important key to understanding why Earth has been able to hold on to much of its water up to this point, while our neighboring planet Venus was not able to do the same. It's theorized that any planet with an atmosphere may also have an electric field. And you may recall that earlier, I said Venus's electric potential was measured to be around 10 volts, roughly 18 times stronger than the ambipolar field on our own planet. While our Earth does lose a constant flow of particles to space, both through the polar wind as well as other types of atmospheric escape, this effect would have likely been much more pronounced on Venus because of its stronger electric potential, leading to the loss of heavier particles, like the ones that make up water. The fact that our ambipolar field is so weak may be an important part of why our planet has been able to hold on to its water. We've only just started to explore depths of how the ambipolar field has influenced our planet and life on Earth, and the Endurance scientists have said there are already plans for additional measurements of our planet's ambipolar field in the future. Like its predecessor, The new rocket will also carry the legacy of a long-past Arctic explorer, named after the Resolute, a ship that set off to explore the Arctic in 1850. Now that we've finally been able to confirm and measure the ambipolar field's strength, and with a follow-up mission already planned to take more measurements, scientists can start asking some of the bigger and more exciting questions, like what it means for Earth's complex atmospheric dynamics, and how it helps to govern planetary evolution. And don't the potential insights we stand to gain from this research feel electric? Once again, thank you all so much for your constant support and for being with us on this journey. Your energy and love are what keep our whole team inspired to keep creating and growing every day. If you'd like to support us even more and unlock some awesome perks, consider joining the channel and becoming a special part of our journey. And as always, if you found this video helpful or entertaining, don't forget to leave a like, share it with your friends, and subscribe so you won't miss any of the exciting content coming up.